Here are a couple of practice synthesis problems. For this first question, we can observe that there are two functional groups here, the ether and the bromine, and they're in a 1-2 relationship, and they are in an anti relationship as well. And those are our clues as to what we want to do sort of as our last step. Remember, we want to work backwards, at least one step backwards, until we can sort of figure out how to get there from our starting material. So what do we know how to put on functional groups in a 1-2 relationship and an anti-relationship? Well, we can do certainly anti-dihydroxylation, but I don't think that's going to help us turn one of those into a bromine. And we know how to do anti-bromination, really. But again, turning one of those into an ether might be a challenge in terms of selectivity, which one reacts and which one doesn't. But similar to the bromination, we know how to put water and bromine together, right? So this is Br2, and water. And we know the water will open up the bromonium cation intermediate. Well, what if we didn't use water? What if we used ethanol instead of water? Then we'd get something that looks like that. And so in this case, maybe the last step looks something like this. And of course, there wouldn't be a lot of regioselectivity here. We would get some ethoxide on that side, but let's ignore that possibility for now. I just made this up right now so we could have some practice. I didn't think for an hour on this problem. So we might have some regiochemical issues, but we could produce this setup here via the bromine addition, and of course we would get to this intermediate. And this then could be opened by the ethanol, right? We could do a backside attack, and we'd get our anti-ethanol. So then the question is, how do I get to this alkene? And I think if you look at it, you might realize that all we need to do is an E1 elimination, just like we did in laboratory. Add a little acid, create water, have water leave. We might get a bit of rearrangement here, so perhaps that's not the right way to go. Let's rethink this. Maybe we don't want to do that, but we could turn this into a better leaving group, and then we could add ethoxide to do an E2, and that would avoid rearrangements, right? Because if we protonated the OH and we lost water, we'd end up with this, and we could do a rearrangement, and that's not going to get us to the product we want. So that's not what we want. I think we want to prevent rearrangements by running an E2 reaction, and that's turning the OH into a better leaving group, tosyl chloride and pyridine, and then ethoxide can be used in an E2 fashion to get us to this alkene. So really it's just, we might call it 3 steps, right? 1, 2, and this one might be 3 in this case. Let's look at the second one. So the first thing that I look at is that I have a chloride on the carbon next to the T-butyl, and now I have the functional group further on down the chain. Do I have the same number of carbons? Well, let's take a look at that. It looks like I still have 5 carbons, so I don't need to lose any carbons. I don't need to gain any carbons, so that can be pretty easy. So somehow I need to get functionality at that end group and turn it into an aldehyde. And there are a couple ways that we can make aldehydes. One of them is just by oxidative cleavage using ozone. Another one is by reacting a terminal alkyne with hydroboration reagents. That's 2 steps, of course. So either of these intermediates here would give me my aldehyde. This one involves adding some carbons only to cleave them off. So that's probably not a very efficient way to do things, and you can probably assume that's not going to be generally our goal in synthesis, to add something only to remove that same something later on. So let's see if we can get to this alkene here as an intermediate. Remember, we have a chlorine on this carbon to start things off. So if we can somehow move that chlorine over, we could do an elimination. And then we could, try to put a group here. Again, we're going to have less selectivity, but we might be able to do something like HBr. Actually, I'd probably rather not do that, because that's going to involve forming cations and potential rearrangements. We do have the possibility for a rearrangement here. So why don't we use BH3 and the rest of all that? I'm not going to write it out here. You can look it up. And that's going to, in theory, give us this OH. And we'll probably get a little bit of selectivity, because there's probably more sterics right around this area than there are right here, because it's further away from that T-butyl group. So I think this will give us some selectivity. And actually, if our next step is tosyl chloride, we can turn that into a tosylate right away. And then we can eliminate. I'm going to move this. Going to move that guy over. So I can eliminate using a large bulky base to get us an alkene closer to our goal. And then we know how to turn an alkene into an alkyne. The first step is adding Br2, and the second step is doing a double elimination. If I can remember the reagent, it's NaNH2, and we need extra of that because we want to do 2 E2 eliminations. So we're going to use excess NaNH2. And then third is simply quenching all this extra base with the water, and that gives us this terminal alkyne. And then we can use this last step here. Let me erase this ozone, because we decided that didn't work at all. So you see there's a sort of a process you go through, but no synthetic problem will be the same as another one. So that's why this is a challenging thought process. And so again, we decided that we knew 2 ways to make aldehydes. We decided this way was the best because it didn't involve adding carbons just to remove them later on. And thus the question then became how to get from this secondary chloride to this terminal alkyne. And really it just involved migrating the leaving group, right? Instead of on carbon 3, we put on carbon 4, and essentially we migrate the double bond at the same time. And once we have a double bond where we want a triple bond, it's just a matter of turning it into a triple bond, adding a couple of bromines, doing a double elimination to create 2 pi bonds, and then we're ready to do our hydroboration on the end carbon. So that's the way to create this aldehyde here from the chloride.